have next time?
Environment.
Environment, sorry, I didn't make you choose. So, let's let Heidi go.
Okay. So I'm going to talk about Milky Way at home, which has been around for a number of years on campus, but hasn't gotten a huge amount of publicity. And so I want to start and end with science. So I'm going to start out with dark matter, so everyone's on the same page and knows why this is important to try to do. And I'm going to talk about measuring dark matter with tidal streams, which is what I'm trying to do, and then Milky Way at home, which is a volunteer computing platform which is in the BCC. It sends out work units all over the world and get a results back. And I have a couple of current results that I'll just put up at the end. So dark matter. If you look at the solar system, all of the mass, pretty much all of the mass is at the sun in the solar system. And if you look at the speed that planets are going around the sun, as they go farther out, they're slower, and it falls off as 1 over the square root of r. That's what we call a Keplerian decline. That's what we expect if all the mass is at the center. Now, this is not what we see in galaxies. This is a rotation curve for M31, and you'll see it's not going down with anything like 1 over the square root of r. This is a picture of M31, and from here to there is 30 arc minutes, which is from here to here on the plot. Let me make that visual for you. So, if all of the matter in the galaxy was stars, or was in some pattern that followed the stars, you'd expect that everything would be within 30 arc minutes, and so you should at least see the Keplerian decline after that. And we don't see that. It keeps going out much closer to flat. And that is the reason that we think that there is dark matter in the Milky Way galaxy. And the idea is you have the light in the center, and then there's this big dark matter halo around it. Okay? And from those rotation curves and from the velocity of stars and galaxies, we can get some idea of how much mass there is. And one of the strange things about dark matter is it's everywhere. It's in this room. It's going through my body. There's probably billions of dark matter particles passing through your body every second, and you don't know it. And when I tell my classes about this, they're like, oh, that's crazy. But there's trillions of neutrinos going through your body every second, so this is not something that's new to physics. And it could possibly be true.
I can imagine that you would have some estimate based on observation how much dark matter there is, but how do you know the size of a dark matter particle?
The mass of it. So you don't know the mass of the particle, so,
How do you know there are billions?
So there are limits on what they should be, and there are expectations from theory for what they should be. But, it could be a different number. But not very far off. Not at this point. Just what people think they are. All right. Okay. So what we don't know about dark matter is astounding. Like we don't know what it is or how to get it or how to find it. No one's ever found one of these. But what's even more astounding is that in the Milky Way galaxy, we have no idea what the distribution of the dark matter in the galaxy is. There aren't a lot of constraints on it. It could be spherical. It could be squashed towards the disk. It could be oblate like a football. It could be triaxial. There are measurements that think it's triaxial. The simulations of stuff from the beginning of the universe give you this big lumpy distribution. And they also, it's likely that the shape changes with time and is different with radius. So there's all kinds of parameters you can try to fit with this to get this dark matter, but not a lot of ways to try to fit those kind of parameters. And the way that I'm trying to do this is through something called tidal streams. Now this movie shows you a dwarf galaxy that's falling into the Milky Way, and as it falls in, stars are tidally stripped off of that, and the ones that come in with slightly lower energies get pulled ahead. They're inside orbits, and these higher energies get pulled behind into these tidal streams. Now, one interesting thing about the tidal streams is that they are the only stars in the Milky Way for which you have information about where they were in the past. And you can, in principle, if we get bigger telescopes and spend more money and better techniques, in principle you can find every star in the Milky Way. You can measure its position, and you can measure its velocity in three-dimensional space. But for none of those stars do you have any idea where they were in the past. And so there's no way to uniquely solve for the galactic potential given that data set, no matter how good you make it. And you can do a thought experiment on this. Suppose that the potential is 0, and you start everything where it is with the velocity it has, and it all flies apart. You have to start making some assumptions about time independence or symmetry or something to start to get idea about what the potential is from the velocity start. When people do that. But we have a unique handle on that potential from the tidal streams, because you know that this star that's on the tidal stream there at one time was on that dwarf galaxy, and so you have an idea where its orbit went, and you'll have a much better handle on what the potential is. Now, we're not good at doing this yet. This is kind of new, and we've had measurements of this, but they've been contradictory, and we're still trying to learn how to best measure the potential using the tidal streams. But there's a good reason to believe that they will be sensitive detectors of the potential and therefore the distribution of dark matter.
And do you know how long ago a given star was in that dwarf galaxy?
We can simulate that. You don't know that without assuming something about the potential, right?
Hey, how confident are people about the models that you're using? You know, things can go wrong in many ways. They can go wrong if you have the right data, the right data at the time or something like that, but they can also be wrong because the models are not right.
The model for the potential.
Yeah.
The model for the potential is completely, that's a big issue, because we don't know what the model is for the potential. In fact, at the conference I was at in August, people were starting to talk about maybe having a orthogonal function expansion and trying to use that rather than trying to fit specific models. But I'm not sure yet if that's the right way to go or not. We're still thinking about how to do that modeling. I mean, the thing is, what we can say now with the data we have is that the simplest model doesn't work.
And isn't it true that even if you collected data, over centuries, it's still such a tiny part of the time frame you're looking at that it won't really be much other than a snapshot of now. Yeah.
I mean, in order to get one of the velocities, you have to have time. You have to look at where it is now and where it is at some other time to get the transverse velocity. But you're just going to get the velocity. You don't get anything about its orbit or the potential.
Just to clear those orbits, you should.
Well, why shouldn't you see that deviation of 1 over r squared even in our solar system?
1 over the square root of r, you mean?
Yeah.
Why should you?
Why should you not? I mean, your first slide was it goes of 1 over distance squared, but then you look far out and you don't see it no more. So why? And then you say there must be dark matter. So why shouldn't be dark matter also in this solar system and make the deviation of 1 over distance squared?
It's 1 over the square root of r. Oh no.
Yeah,
So if you have a point, if you have all of the mass at the center of the system, then Kepler's laws, just basic physics, tells you that the velocity. First, if you have a circular, just imagine you have circular orbits, makes it easy. If you have a circular orbit, then in order to stay in that circular orbit, the velocity falls off. The velocity has to be different by 1 over the square root of r as far as you go away. So that's the central thing. And so if you see a case where that does not happen, then it tells you that the mass is not all at the center.
I think he's asking.
No, but then you said, well, then there's something wrong, and then there must be dark matter. And then you say dark matter must also be everywhere where we is, and therefore, why is it not affecting us in the solar system?
There is dark matter in the solar system, but it's basically uniform over the solar system. And so
Is the point that it's weak compared to the gravity on the scale of the solar system?
what's that?
Is the point that the dark matter that's in the solar system is weak relative to
Right.
gravity on the scale of the solar system, but not on the scale of the galaxy?
Right.
I think if you calculate the mass of dark matter in the solar system, it's much less than the solar mass.
Right, and it's spread everywhere, so you're not gonna, there's no effect.
It's transparent.
Yeah, we don't notice because it's very, it's not a significant fraction of the mass in the world. It's very, very, even though we're all a lot apart.
Real small.
Space is big.
All right, so we get the stuff going around. I mean, this is a picture where the dots in this picture are actual data. These are M giant stars in the Milky Way. There's the galactic center. There's a bunch of stuff here because we can see stars close to us better. That's what it is. And here's a dwarf galaxy, and here's the stars coming off the big tidal tail. direction. That's the largest of the tidal streams in the Milky Way, the Sagittarius IV tidal stream. So what I'd like to do is to use these tidal streams to measure the to constrain the potential of the Milky Way. And so what we need to do is to measure the spatial density as much as we can for these tidal streams and velocity information. There are now a dozen known tidal streams in the Milky Way, bigger ones, smaller ones, some dwarf galaxies, and some are globular clusters. But we get as much information as we can about those streams, and it's actually complicated. As Fran was pointing out, we have had issues where tidal streams, there's actually more than one tidal stream in a place that we thought there was one. So, piecing that out is another, big process on them. So we're working on that. Then you define a bunch of parameters. You have the orbital parameters and internal properties of the dwarf galaxies. So that's 11 parameters for each tidal stream, plus the time it's been in orbit. And then you have parameters for the spatial distribution of dark matter, and as Fran pointed out, that could be any number of parameters or models to try to put that together. And so you make simpler ones and more complicated as they don't work.
And they're all static, right?
They are static. I would like to, so if you look at models for the evolution of the Milky Way, we expect that over the last 3 billion years it hasn't changed too much on grand scale. But on small scale, it clearly has, because we know that there are dwarf galaxies that are in orbit around the Milky Way, and they can interact with each other, and they could potentially change the orbits of each other, which will change the tidal streams.
Right.
And so I would like to...
200 billion years for the orbit?
Half a billion. So I would like to be able to put in the time-dependent part, at least for smaller lumps. I don't think at this point I'm looking at doing time-dependent of like from the beginning of the universe, but for lump interactions, that kind of time dependence, I would like to try to put that in. And then what we're doing is we have this data, and then we want to run n-body simulations of the tidal disruption of the dwarf galaxies in this parameterized potential. And then you optimize the parameters so that the simulations match the data. Now, to do one of these simulations for one dwarf galaxy on one CPU is 30 minutes, just to give you a time scale of what it is. When you add up how many parameters in the long run we want to try to be able to do, this is a big problem. And one of the things about big data, so I was involved in big data in astronomy with the Sloan Digital Sky Survey. This is the classic big data project that people work on. And the thing that I've come to understand about big data now is when you have big data, your models don't work. I mean, the models that we were using originally with the Sloan data to try to fit this were 2-parameter power laws to fit everything, because we didn't even know there were tidal streams out there. Okay? And now we're looking at hundreds of parameters. Actually, it's more than that because we have a lot of parameters for the streams. But we're trying to fit an enormous, more complicated models. And in order to do that, you need big compute. And so really where I am at in the big data paradigm is going from big data, which we've actually, in astronomy, mostly we've learned how to store it and access it, and we can mostly do that. And now what I'm trying to do is to make our models fit it, which is requiring big compute.
So Heidi, you can do big compute, as you know, on supercomputers in the cloud, citizen stuff, which you do too. And it depends on whether you have big communication really or not.
That's right.
For your n-body stuff, are there versions you can do in the cloud and stuff like that?
So we haven't done this in the cloud. I mean, Carlos has talked about this. We have done it on the supercomputers on campus. There are limits to how many different platforms I can do it on because I have a very limited number of people to put onto the project. And this is the direction that we're working on now. I'll show you how Milky Way at home works. I think it'll answer the other question about communication. So, big compute. Milky Way at home, it began in November 2007. we had a grant, an NSF grant between myself, Oleg Szymanski, Carlos Varela, and Malik Mektanizma in computer science to work on parallelizing some of the model fitting that I was doing in astronomy that was not working because it was not converging because it was not parallelized. And out of that grant, Milky Way at Home was made. It currently runs about half a petaflops. There was, when we first put GPUs on it, it went up to 2 petaflops because we were the only GPU experiment out there. So we actually beat the campus in getting to petascale. The total number of people that have volunteered their computers all over the world is about 150,000. Now up to 170 since these numbers were 170,000. There were 100 people a day join Milky Way Home, some number of these. So we have about 25,000 people at any time who are volunteering their computers. And we have 2 applications that are running. One is a maximum likelihood fit to fit the density structure of the tidal streams. Because you need to do that. That's actually a complicated large parameter problem to fit that density structure. And then we're also have a fledge, and that's been running for a number of years and is now starting to turn out the results. We also have a new application, which we're just getting our feet wet in fitting the n-body simulations to those tidal stream characterizations. And that's, there's a whole algorithm development procedure to figure out how do you take the output of an n-body model and match that to stars, because they're not going to be in the same place, right? You just want the distribution of them to be similar. So comparing those distributions is a whole other ball of wax. So Milky Way at Home, basically, from the astronomy students' side, our job is to write an algorithm. So you have your data, and you have your model, and then you have to write some sort of goodness of fit that tells you, does this model fit this data? Right? So you have to have some measure of goodness of fit. Milky Way at Home itself is an engine for optimization. That's really what it is. It actually doesn't have too much astronomy in the Milky Way at Home server at all. It's all about optimizing parameters. And so what happens is we built this, we have a server in VCC, and we give it this algorithm, and we say, okay, and then it has another set of software that does the optimization. So we can do particle swarm, and what was the other one that we're doing?
Differential evolution.
Differential evolution are the 2 that are working on it now, and there's a whole, we've had different kinds that we've been working on, but that was done mostly by Travis DeSalle, who was a graduate student in computer science, who's now at North Dakota, making a career in doing at-homes and optimization problems on at-home. So anyway, so this is a bit of a challenge for us in astronomy, but I think we finally figured out how to do this, because we write these algorithms and we have to put them on the server, and then this code is farmed out to people all over the world. So we compile for 15 platforms. So that's Mac, Windows, Linux, 64-bit, and 32-bit, except for we don't have 32-bit of Macs. So it's 5 platforms, and then there's CPUs, and there's 2 kinds of GPUs. So it's 15 platforms. Has to work without crashing or causing any trouble on computers all over the world. And so this is a process where you put it out and you have to pull it down a couple hours later because there's some bug that you couldn't find in our development system and put it back. Jake is looking at me like he knows exactly what the problem is.
So each computer out there calculates the likelihood for the full data set for one
set of parameters. Right. So we send out parameters to each of everybody all over the world. But some people have big computers, some have little ones, and whatever kind of computer that's out there. We'll send it out to each of those, and then they'll come back and say, here's the measure of the goodness of fit. And then optimize here. What's that?
How much data are you sending out? Very much? Not very much?
We send out not very much data.
So this model works because those 25,000 or whatever computers at any one time, there are enough different parameter sets.
Oh, there's a lot of parameter sets. We got a lot of parameters to twiddle. We can keep them all busy, no problem at all.
So, yeah, so, all right.
And we have, probably you know, order 10 jobs running at the same time, so, you know, we've got.
A different
People doing all
model would have been
different.
to calculate one parameter set at a time and send it to everybody when that parameter
A lot
set
of
is done.
communication.
So that just doesn't work because of the communication overhead.
It's asynchronous. So what happens, I mean, you send a job to this guy, and this guy's got a little CPU computer, and he turns it off all the time. He has other things running on it, and he's gonna come back in a week, and then he went on vacation so it's actually 2 weeks. So he sends it back 2 weeks. This guy's coming back in 10 seconds.
Sure.
And
So it's driving this in the
completely
parameters, not
asynchronous.
the data.
Well, and the, you know, as Heidi says, it's asynchronous, and you have to worry about, you know, what if some guy's computer crashes, and then, you know, is there a hole in the data and stuff.
There's all kinds of
Yeah, it's
issues.
really interesting.
Yeah, you can deal with a missing parameter calculation.
It's incredibly interesting.
Yeah, you're missing a piece of your integration over the likelihood buying your kind of host. All right, so with this 150 volunteers, we've learned a lot. These people let us use their CPUs or their GPUs. They're continuously upgrading their hardware, so there's like, we don't have to do hardware upgrades. We don't have to have, I mean, every few years we need maybe a new server, but we don't need to replace the whole 69. They extensively are involved in forum discussion with science, technical support, and you can pretty much find discussions on anything on there. They monitor the health of the system. I mean, I get email from our volunteer moderator if things are messing up. He sends me email. He sends it to these guys, and if they don't respond quickly enough, he sends it to me. He says, "Oh, there's a problem. You need to get on this." One of our volunteers wrote the first version of GPU, the GPU version, before I even knew what a GPU was. I never heard of this, and they said, "Hey, look at this! It runs a lot faster on a GPU." So that happened, and they donate a small amount of money, and they donate hardware. Particularly if we don't have a version that worked on their hardware, they gave us hardware so that we could try to make it work on that.
Is this open source?
What's that? Open source. It's open source. That was a decision we made. Actually, we made that decision after the GPU person, because the person who wrote the GPU code got the code from us, you know, privately. Rewrote it for GPU, and he rewrote it for GPU so that he could crunch work units faster than anybody else, which made everybody else really angry. And so we said, okay, fine, we'll just This is a heat map of where most of our computers are in the U.S. and in Europe. And they're really every country in the world. There's countries I never heard of. This is the top 27 list of countries. You see China. So we're working now on I'm doing an advertising campaign in China next week. But you know, if you look at the bottom of the top 100 list, I mean, there's just I don't even know where some of these places are. So they're pretty much everywhere. Okay, there's like 200 anywhere, Aruba. And this is not, I mean, it goes down to, this is the top, it goes down to 211, you know. And those places are really tiny. And
Is there a country that is not?
No, every country. You know, every country. So we put news up on MilkyWay home websites, we have message boards, we have science pages, we have our own YouTube channel. We have an article in this month's issue of Amateur Astronomer in China. They have a grant to build a Chinese language website version of MilkyWay at Home. I'm going to give next week a public lecture at the Beijing Planetarium that's associated with that grant. We're working on badges and credits for credits and donations. And I would like to in the future, and we have not gotten this funded yet, I'd like to have volunteers be able to choose their own parameters. Because as it is now, it's not exactly citizen science, because they're just volunteering their computers, but if they had a chance to try to affect the results, that would make it a real citizen science project. So just at the end, I want to put up a couple results from the two different applications that I have up. One of them is, this is the density map of turn-off stars in the Sloan Digital Sky Survey in the North Galactic Cap. All right, so that's 2 million turn-off stars that we've got in there. And then we run it through MilkyWay Home, and we do it one stripe at a time. going through this data and put it all together, and then we're able to now, when we have the density map of the stream and the stuff that's not the stream, we can go and pick up every star, star by star, and say what's the probability in the stream or not in the stream, and put it in 2 different categories. And so we can now pull out a set of stars that has the density of the stream, and then do whatever measurements we want on that to get our density map of the spatial structure of the streams. And then we can now take this and fit that stream there and this one over here and bring them out one by one and build up a self-consistent 3D map of all the substructures in the halo, which is what we're working on right now. And from the n-body, we only have a piece of the n-body coded. And the piece of it allows us to fit only the properties, the internal properties of the dwarf and the time that it's been evolving through the galaxy. And we're using the density of stars along the stream from the data to compare to the density of stars along the stream from the model. And we use an Earth Newberg distance to compare those results. And so we're trying to figure out if we can determine whether there is dark, I'm really done. So we're trying to determine whether there's dark matter in the dwarf galaxy from the distribution of stars along the stream as the first step in this. But there's all kinds of extensions to put more parameters and more dwarf galaxies and whatever. And we do have some preliminary results that show that if we put in a simulated density along the stream for some particular galaxy, we're able to, for most parameters, we're still working, I think there's some bugs for the other ones, but we can pull out the properties of the dwarf galaxy. So at least we have one example in this case. And that is all I have to present. This is a list of people who have worked on Milky Way, and it's actually a very skeleton crew for how much work it is to make this work. Yeah.
Do you have credits for software development?
We have not yet. We've only had people within my group, graduates of people in my group, and this one guy, I think, do software development that I'm aware of.
Seems like you've got a lot of labor you could tap into.
Well, potentially we do. I mean, they're
There's a
actually
challenge
very
with that
interested
because
in it.
Boeing credits actually are across all projects. And they want a Boeing credit to have some relationship to FLOPS.
Yeah, but we could give out badges for software or something, I suppose.
Yeah, badges
For
are
software
credit
development.
is not okay to be for software.
Or call it something else. Then if somebody's willing to work for some very abstract thing like that.
Yeah.
Well, the GPU guy did the GPU program, is he an author on papers?
He's a co-author of it.
Okay, so it could be interesting to people who want to have their name inside the basis.
It's very cool. So cool that I'd like to promote you to full professor.
Second.
You already are, aren't you?
Yeah.
Oh, that's what you're making fun of. You listed yourself as associate professor.
Oh, sorry. Why does that say that?
What ranking are you within the Boeing applications? Who's not?
It's like 6th or something?
Really?
6th most popular.
We're in the top 5.
It's been
Any other astronomy ones in the first 5?
SETI.
SETI's big.
Oh, SETI for sure, yeah. But you actually have results, SETI doesn't have any positive results yet.
What we do
They haven't
is
done
way
about
more
that
complicated also. What we're doing is way more complicated than SETI.
Oh, yeah.
SETI is almost, because, I mean, this whole piece of having the optimizer, it's a really big deal to do the optimization.
Wow, that's pretty amazing to be number 6.
I think we were higher at one time, right?
We're not gonna want
too.
They have like folding at home must be at the top of
Yeah.
mine.
Klotz conjecture is way up there for some reason, I have no idea.
Heidi, now you have to repeat the experiment, close the loop. Galaxy or universe. Show that it works.
That's places to run home.
Men in black.